recall certain things before I continue. So you see, at this point we are trying to show that the the modular function j tilde is one to one on the region, the fundamental region script d. So in fact the statement that script d is a fundamental region for j tilde involves the verification that j tilde restricted to script d is injective, okay, which is what we have to prove. So let me again let me recall very quickly certain things to just set up the notation, just recalling notation. So you see, if you recall, we start with tau in the upper half plane, and then you end up with so you have the lattice defined by tau, which is the set of all n plus m tau, where n and m are integers, and then you have the torus defined by tau, which is the complex plane modulo this lattice, okay, and so you get a map from u to u mod PSL2Z, tau going to isomorphism class of the torus defined by tau, okay, and so if you recall, two elements tau 1 and tau 2 in the upper half plane will define holomorphically isomorphic tori if and only if tau 1 and tau 2 differ by an element of PSL2Z, the unimodular group, okay. These are Mobius transformations which when written in matrix form have integer entries and determinant 1, okay, and of course this is a subgroup of PSL2R, which is the full group of automorphisms of the upper half plane, and we were trying to show that u mod PSL2Z is biholomorphic to C. So what we did was we defined the function j tilde, a holomorphic map j tilde, and we proved that j tilde goes down to a map J, that is this diagram commutes. So this j tilde was invariant under the full modular group, and let me quickly recall how we got hold of this j tilde, we will need it. So given tau, we have the Weierstrass phe-function, have the phe-function phi tau of z, it is a doubly periodic function and an elliptic function of the simplest kind with a 0 of order, with a pole of order 2 at every point of this lattice, and it is defined by series expansion. And then we found that this phi function satisfies a differential equation. The differential equation was phi tau prime of z, the whole cube is 4 into p tau z, I think this was squared and this was cubed, minus g2 p tau z minus g3, where g2 and g3 are functions of tau, and what we did was, so this is the natural differential equation that the Weierstrass phi function satisfies, and we also factorized the right side because it is a cubic, you have 3 linear factors, and we factorized it as follows: phi prime tau sub z whole squared is 4 times phi tau of z minus E1 into phi tau of z minus E2 into phi tau of z minus E3, where of course E1, E2, E3 are also dependent on z, I mean also are dependent on tau, and they are the zeros of the derivative of the Weierstrass phi function. And in fact we found that there are essentially 3 zeros within a period parallelogram, and these are given by so we set E1 to be phi tau of half, E2 is equal to phi tau of tau by 2, and E3 is equal to phi tau of 1 plus tau by 2. So within the fundamental parallelogram which has vertices 0, 1, tau and 1 plus tau, these were the 3 zeros of phi prime, and we set E1, E2, E3 to be in this way, and this gives rise to a function lambda. So we have this helps us to define a function lambda on the upper half plane with values in the complex numbers. It is a holomorphic function, and the function lambda is defined by lambda of tau is equal to so it was I think E3 of tau minus E2 of tau by E1 of tau minus E2 of tau. So well I mean that is right, and well so the point is that as tau varies as tau varies E1, E2, E3 also vary, okay, and that is how we get lambda as a function on the upper half plane, okay. Here tau is varying, and lambda is holomorphic, lambda is not equal to 0, 1 or 1, okay, and of course and lambda is invariant under the congruence mod 2 subgroup PSL2Z sub 2. PSL2Z sub 2 is the normal subgroup of PSL2Z consisting of matrices with entries which give the identity when you read the entries, each of the entries mod 2, okay. So this is the congruent mod 2 subgroup, and lambda is invariant under the congruent mod 2 subgroup, but actually what we are looking at is we want a function defined on this, namely you want a function defined which is that, therefore this should correspond to a function j tilde which should be invariant under the full modular group, okay, but this is only a partially modular function. It is only this is a modular function which is defined, which is modular only for the for this particular subgroup, congruence mod 2 subgroup, but you want a function which is invariant under the whole unimodular group. So we define j tilde of lambda to be 4 by 27 into lambda squared, so j tilde of tau to be 4 by 27 into lambda squared tau minus lambda of tau plus 1 the whole cube by lambda squared of tau into 1 minus lambda of tau the whole square. We defined this function j tilde, and what we proved was this, that j tilde of tau is see, since lambda is not equal to 0 or 1, the denominator never vanishes, and since lambda is a holomorphic function, j tilde of tau is also holomorphic, and this function is the function that we want, namely the one that is invariant under the full unimodular group. So it is PSL2Z invariant, okay, and what we have already shown is of course you can recall that this set, the set of orbits of PSL2Z in of the group PSL2Z in U can be identified with the set of holomorphic isomorphism classes of complex tori, and this is not just a set, this is a Riemann surface. We proved that, we have proved that earlier, namely we proved that this group PSL2Z, the action of this group on the upper half plane is actually a properly discontinuous action, and then therefore when you divide by a when you take a quotient by a group with the properly discontinuous action, then the quotient can also be given a Riemann surface structure. So this becomes a Riemann surface structure, and if you remember, the way we proved that PSL2Z acts properly discontinuously on U was by proving that PSL2Z is actually discrete. Of course it is discrete because it has entries in the integers, but the more important thing is that it is that it leaves the upper half plane invariant. So it's you know it's a Fuchsian group, and then we know that for a Fuchsian group, I mean for a Kleinian group, I mean for a Fuchsian group, discreteness is equivalent to the group acting properly discontinuously on the half plane or the disk which the group leaves invariant, because by definition a Fuchsian group is a group which leaves a half plane or a disk invariant, and PSL2Z is certainly a group of Mobius transformations that leaves the upper half plane invariant. So it is a Fuchsian group, and it is discrete. So the discreteness is enough to conclude that PSL2Z is acts properly discontinuously on U, and then since it acts properly discontinuously on U, the quotient becomes a Riemann surface such that this mapping, canonical quotient map, becomes holomorphic. So this is a Riemann surface, and our aim is to show that this Riemann surface is isomorphic to C. Namely, we are trying to say that for every holomorphic isomorphism class of a torus, there is a unique complex number, and that complex number is called the j-invariant of the torus. So one single invariant is enough to classify all the holomorphic isomorphism classes, that is to classify complex tori up to holomorphic isomorphism. A single invariant is enough, a single complex invariant is enough, that is the statement. Okay, so we want to show that this is holomorphically isomorphic to C, so we are looking for a function j which is a bijective holomorphic map. Okay, but a function like this will come from above, because if you give me j, then I can take the composition, call that as j tilde, and j tilde will obviously be PSL2Z invariant. Conversely, if I have a j tilde which is PSL2Z invariant, it will go down to a function j. Okay, therefore we have to find this j tilde, and here it is. Okay, now we will have to prove a couple of things, namely so we have to prove that j tilde is so we have to prove that this j is both surjective and injective. Okay, the surjectivity has already been proved. Okay, essentially because of the use of the fundamental theorem of algebra. Okay, j tilde we have shown, so let me write that down. J tilde is surjective, that has already been proved in an earlier lecture. So now I will have to draw some diagrams to tell you about the injectivity. Does not come out in a straightforward way. So the point, the key to finding the injectivity is to look at the fundamental region for j tilde, which is and in fact what we are actually trying to show is that the fundamental region of j tilde is the same as the fundamental region of PSL2Z. Okay, so I will have to draw a diagram. So let me draw it. So we have basically, if you remember, so let me draw it somewhere, because I need to use it again. So let me draw it here. Okay, so you see, so we have, so this is the tau plane, this is the real axis, this is the imaginary axis, and well, basically we take I think I will need semicircle of radius 1, so let me draw it here so that I have enough space. So this is half, so here is this well, so this half, this is 1, so this is I. So you see I draw this semicircle centered at half, radius half, so I get this. Then I do the same thing at minus half, and I end up with this semicircle, and then I also draw circles of radius 1 centered at 0, 1 and minus 1, so I'll end up with okay, so I'll have one like this, and then I'll have one more centered at minus 1, so I'll have to draw these vertical lines, so I'll draw one vertical line here, then I have another vertical line here, and I have circles centered at minus 1, radius 1, so I'll get something like this, and I'll have a circle centered at 1, radius 1, that will go like this. Okay. So and then I draw this vertical line passing through this point half, so but I draw it only up to this, and similarly I draw another vertical line like this. Okay, and the you see this whole region was called as omega, okay, and this region was called as omega prime. So let me because I am going to write several things on this diagram, let me explain. Omega is the interior of the region bounded by this line, and this semicircle. Okay, so all of this is omega, and omega prime is just its reflection about the imaginary axis, namely omega prime is the open set bounded on the left by this line, on the right by this line, and below by this semicircle. All right, and then we also gave, and what was special about this omega and omega prime was that we proved that this function lambda actually maps omega holomorphically onto the upper half plane, and it maps omega prime holomorphically onto the lower half plane. So let me write that down. Lambda from omega to u is a holomorphic isomorphism, and lambda from omega prime to minus u, by minus u I mean the lower half plane, okay, that is also a holomorphic isomorphism. And in fact we also proved that lambda is can be extended continuously to the boundary of omega, and it is monotonic, and what you get is lambda from actually I think if you take omega bar union omega prime, okay, what I will end up, and of course when I take omega bar, that means I am taking the closure, so I will get the points 0 and 1, okay, and I think so this will correspond to so lambda as you go higher up, the lambda values will go to 0, and at 0 lambda takes the value 1, and at 1 lambda takes the value infinity. Okay, so I will end up so this should give me yeah, anyway, yeah, let me not worry about that immediately. So I want you to know, remember this. Then we had this other important thing, and then we also had that see lambda was only invariant under the congruence mod 2 subgroup, and we wanted to know how lambda behaved under a general PSL2Z element, and therefore that led us to write out certain functional equations on lambda. Okay, and if you remember, these functional equations were based on a set of say 6 Mobius transformations which gave a complete set of matrices in PSL2 Z mod 2Z. Okay, so if you remember, so let me write down certain things. So let me write down certain the following Mobius transformations, so that I mean it's so you see we have, so let me write this down here. A1 of tau is tau, this identity, and A1 inverse is of tau is just again tau. Then A2 of tau is the Mobius transformation tau plus 1. A2 inverse of tau is of course going to be tau minus 1, and well, A3 of tau was minus 1 by tau, and A3 inverse is same as A3, and A4 of tau was minus 1 by tau plus 1, and A4 inverse of tau was A6 of tau, where I will define what A6 is. A5 of tau was tau by tau plus 1, A5 inverse of tau was is tau by 1 minus tau, and A6 of tau is 1 by 1 minus tau. A6 inverse of tau is just A4 of tau, because A4 inverse is A6, A6 inverse is A4. Okay, and the point was, if you take 6 of these, then mod if you read them mod 2, you get all the 6 elements of PSL2 with entries in Z mod 2Z. Okay, so that is entries 0 or 1. Okay, and then see, we studied the certain mapping properties. You see, in fact we called this region as delta. Okay, and then we call this region as this open set as delta prime. So what is delta? Delta is the open set which is bounded by this ray and this portion of the unit circle, and then this ray. Okay, and then delta prime was its reflection under the imaginary axis, namely the open set that is bounded by this ray, this segment of the unit circle, and this part of this ray on the imaginary axis. And what we actually proved was, if you remember, we proved, we checked out that these fellows map these 2 regions onto the total 12 regions that are there in this, if you forget the regions enclosed by the semicircles. And well, it's easy for you, it's an easy exercise for you to check that this is what you get. So you see, this is delta, this is A2 of delta, this is A2 of delta prime. Okay, and this is A2 inverse of delta. Okay, and this is A3 delta, and this is A3 inverse of delta. Okay, okay, then this is A4, this is A4 of delta prime, and this is A6 inverse of delta prime. A6 inverse of delta, and this is A5 of delta, this should be delta prime, and this is A4 inverse of delta, and this is A6 of delta prime, and this is A5 inverse of delta. Okay, so you see basically what is happening is, you see if you take A1, A2, A3, A4, A5, A6 and apply it to delta prime, you get A1 of delta prime is delta prime, A2 of delta prime is here, then you have A3 of this must be A3 of delta prime, this should be prime, this is A3 of delta prime, then you get A4 of delta prime, then you get A5 of delta prime, A6 of delta prime. So in fact, so you know, if you shade it like this, essentially you get these things, namely you get this. So basically you see this A1 through A6 map delta prime onto these 6 shaded regions. This is A1, this is image of A2, this is the image of A3, this is image of A4, this is the image of A5, this is the image of A6, and what is happening to delta, the inverses, A1 inverse through A6 inverse, that maps delta onto the unshaded regions. So this is A1 inverse of delta, which is the same as A1 of delta, which is identity, this is A2 inverse of delta, this is A3 inverse of delta, okay, this is A4 inverse, this is A5 inverse, and this is A6 inverse. Okay, so all these, so this is how all these 6 transformations and their inverses map this region. Okay, and they are all, because they are all Mobius transformations, the mappings are conformal, and the boundaries are mapped to the boundaries and so on. Okay, so we will need this actually, so that is the reason why I am taking some time to recall this. Now you see this region was called as script D. So script D is somewhere here. I mean basically it encloses the interior of this region bounded by this vertical line segment, this vertical line segment, and this arc of the unit circle, and then in the boundary you take only this part and this part. Okay, that was your script D. Okay, and so if I draw that separately, script D is basically this. Well, so you know, so my script D is actually this. So I put dotted lines here so that I'm removing the boundary, and I remove this, and this is script D. Okay, script D is essentially this region. Of course, you see this this point is I. Okay, that is, this point is I, and this point is a complex cube root of unity, and this is its mirror image. Okay, and so on. So so the fact is that what we have already shown is that this script D is a fundamental region for the action of PSL2C. Okay, what does it mean? It is if you recall that, it means that for every orbit of PSL2Z in the upper half plane meets this fundamental set at exactly one point. Mind you, it's not an open set because I have included part of the boundary, and the reason why I am not including this part of the boundary is because the values taken by lambda here are the same as the values taken by j here are the same as the values taken by j there, because it is translation by 1. Okay, and j is invariant under PSL2Z, and translation by 1 is a PSL2Z element. Okay, so this set is actually a fundamental set for PSL2Z that we have proved. Okay, in fact the way we proved it was we showed that first of all we proved that any PSL2Z orbit has to intersect this. That is the first step we proved, and then we proved that if there are 2 points here which are such that one point which belong to the same orbit under PSL2Z, then they are one and the same. That is what we proved. So we proved that this is a fundamental region for PSL2Z. So then the other thing that we proved, so the other thing we were trying to prove was that for J tilde also this is a fundamental region. Okay, what does that mean? It means that you have to show that J tilde restricted to this is both injective as well as surjective. Okay, of course surjectivity is already done. Alright, basically J tilde is surjective from the J tilde is surjective from the upper half plane. So but then give me any point in the upper half plane, there is a representative in its orbit here, and J tilde will take the same value here. It will take the same value throughout the orb at every point of an orbit because it is invariant under PSL2Z. Therefore the fact that J tilde is J tilde from U to C is surjective will tell you that J tilde from script D to C is also surjective. Okay, so let me write that also somewhere here. Script D is a fundamental region or set for PSL2Z, and J tilde restricted to script D is surjective. Okay, so therefore the only thing that is left out to be proved is J tilde restricted to this script D is injective. Okay, which is what we have to prove. Once you prove that, then it will follow that this J is a bijective holomorphic map, and you know this is a Riemann surface, that is a Riemann surface. The bijective holomorphic map is holomorphic isomorphism. Okay, and that will have proved to you that the set of isomorphism classes of complex tori, there is a natural Riemann surface structure which is none other than the usual Riemann surface structure on the complex plane. Okay, so I will have to prove that J tilde restricted to script D is injective. Okay, so how do I do that? So for that, so that also involves a little bit of clever computation. Of course it's not that it looks clever, but it is it's not a trick. It's backed by some phenomena which are occurring in the realm of Galois theory. Okay, so there is a certain Galois theory which is going on. You can look at it as a Galois theory of Riemann surfaces, or you can also look at it as a Galois theory of fields. Okay, but then I don't want to go far afield, but I am going to write down now certain things which may seem magical, but essentially they are not tricks. They have come because of delving into some Galois theory. Okay, so let me explain. So what we are going to do is we are going to consider you see the point is that the analytic properties of J tilde, the mapping properties of J tilde are completely controlled by those of lambda, because J tilde is PSL2Z invariant. Okay, and how lambda behaves we know very well, because you see if you know how lambda behaves with respect to these, then you know how lambda behaves with respect to any element of PSL2Z. Okay, so you see we already know in some sense the mapping properties of J tilde, but the important thing is that there is something algebraic going on. The important thing is that you should look at J tilde not as a function of tau, but look at J tilde as a function of lambda. Okay, so what we will do is consider J tilde as a function of lambda. Okay, so basically you define J, so I will define small j of lambda by the same formula 4/27 into lambda squared minus lambda plus 1 the whole cube by lambda squared into 1 minus lambda the whole squared. Okay, then you see this J is actually a map from the complex plane minus 0 comma 1 to the complex plane minus 0 comma 1, okay. So J is a holomorphic function on C minus 0 1, okay. J is a it's a holomorphic function. In fact, it's a rational function. It's a quotient of polynomials, okay. So it's a holomorphic function, so rational function on complex plane minus 0 1. I have to exclude the values 0 and 1 because the denominator vanishes, but then if I think of it as a rational function, then I can think of it also as a function from P1 to P1, namely at 0 and at 1 I can define the value of the function to be infinity, and at infinity also I can define the value to be infinity because the numerator is a higher degree polynomial than the denominator polynomial. So you see, so it's a holomorphic function on this, it's a rational function on P1 with values in P1. So if you want, P1C is just the Riemann sphere, it is the natural Riemann surface structure on the extended complex plane, the complex plane along with the point at infinity, which you get a Riemann surface structure homeomorphic to the real 2 sphere via this stereographic projection, okay. So that is P1C, and so either you think of J as a function on C minus 0 1, or you think of it as a holomorphic function on C minus 0 1, or think of it as a rational function from P1 to P1, okay. Now the key to the injectivity of J tilde is the following statement, theorem. J of lambda 1 is equal to J of lambda 2 for lambda 1 comma lambda 2 in C minus 0 1 if and only if lambda 1 belongs to the following set, lambda 2 1 by lambda 2. So let me write out the set of things they have. 1 minus lambda 2 1 by 1 minus lambda 2 lambda 2 by lambda 2 minus 1 lambda 2 minus 1 by lambda 2. So this is the theorem, okay. So the Galois theory is that what is actually happening is that from C there is an action of I will try to give this in the exercises, or if I have time I will expand upon it at the end of the lecture. There is an action of the symmetric group on 3 elements thought of as a symmetric group on acting on 0 1 and infinity, I mean 0 1 and lambda, okay, where lambda is in lambda is a complex number not equal to 0 1, which for that action this is the orbit of for a given lambda, the orbit is given by lambda 1 by lambda 1 minus lambda 1 by 1 minus lambda lambda by lambda minus 1 and lambda minus 1 by lambda, and what happens is this map from C minus 0 1 to C minus 0 1 is actually a covering, it is a Galois covering, okay, and of course it is a ramified cover, it is a ramified holomorphic covering, and if you look at it as a covering of the meromorphic functions on P1 over the meromorphic functions on P1, then it is actually a Galois extension, and the Galois group is actually the symmetric group on 3 elements, okay. So this is the Galois theory that is involved, okay, which gives rise to this I mean it gives the which gives us the statement of this theorem, okay. So but before so my claim is if I prove this theorem then we are done. So let me first get that as a corollary, let me first prove the corollary to the above theorem. It is J tilde restricted to D is injective. So the corollary to this theorem is J tilde restricted to script D is injective, okay. So how is that true? So the proof of corollary see what you will have is, see if j tilde of lambda of tau 1 is equal to j tilde of lambda of tau 2 where tau 1 tau 2 are in script d, okay, we set lambda of tau 1 as lambda 1, lambda of tau 2 as lambda 2, okay, we call lambda tau 1 as lambda 1 and lambda tau 2 as lambda 2, then what you will get is, well then you see what you will get is j small j of lambda 1 is equal to small j of lambda 2, because you know after all small j is just capital J thought of as function on lambda, okay. So you get j of lambda 1 equal to lambda j of lambda 2, so what you will get is that you will get either, so you will get lambda 1 belongs to all these things, I mean lambda 2, so lambda 1 is equal to, well, lambda 2 or it is 1 by lambda 2 or so these are the various possibilities, so let me write it like this, lambda 1, let me write out all those possibilities, lambda 2 by lambda 2 minus 1, lambda 2 minus 1 by lambda 2. So these are the 6 possibilities for lambda 1, okay, that is because of this theorem, okay, and now we will have to reinterpret this using these mapping properties. See actually if you check see so let me write this down, so you see this lambda 2 is just a1 so it's it's lambda 2 is actually lambda of tau 2, lambda 2 is just lambda of tau 2, okay, and by the way the thing on the left side is lambda of tau 1 which is lambda 1, okay, and here I have lambda of tau 2, and what is lambda of tau 2, well if you want you can write this as a1, it's yeah lambda of a1 of tau 2 and is also lambda of a1 inverse of tau 2 because a1 and a1 inverse are one and the same, okay, lambda of a2 of tau is was lambda tau by lambda tau minus 1, okay. So I am writing down these functional equations that we proved several lectures ago, lambda of a2 of tau is lambda tau by lambda tau minus 1, lambda of a3 of tau is 1 minus lambda of tau, lambda of a4 of tau is it was lambda tau minus 1 by lambda tau, lambda of a5 of tau is going to be is 1 by lambda tau, okay, and lambda of a6 of tau lambda of a6 of tau gave me 1 by 1 minus lambda of tau, okay. I mean these are essentially the things we have to use diligently, alright. So now you can more or less I think several of them can be written down directly. So you see this is 1 by so yeah I think several of them can be written down directly from the table. This is 1 minus lambda of tau 2, okay, but 1 minus lambda of tau 2 is lambda of a3 of is lambda of a3 of tau 2, okay, and a3 is the same as a3 inverse, so this is also lambda of a3 inverse of tau 2, A3 is its own A3 is A3 yeah, A3 is its own inverse, okay. So I can write that, and see 1 by 1 minus lambda 2 is of this form, so it is lambda of A6 of tau 2, so it is 1 by 1 minus lambda of tau 2, this is lambda of A6 of tau 2, and this is of course lambda of A4 inverse of tau 2, because A6 is A4 inverse and A4 is A6 inverse, okay. Then lambda by lambda minus 1, lambda 2 by lambda 2 minus 1 corresponds to this one, so this is lambda of tau 2 by lambda of tau 2 minus 1, and this is lambda of you see lambda by lambda minus 1 is lambda of A2 of tau A2 of tau 2, okay. And now I want to say this is also equal to lambda of A2 inverse of tau 2, because A2 squared is congruent to 1 mod 2, is congruent to the identity mod 2, see, so this will also be lambda of A2 inverse of tau 2, so I owe you an explanation here, because you see if you take A2 of tau is actually what, A2 of tau is tau plus 1, okay. If you calculate A2 squared of tau you will get tau plus 2, okay, and this will correspond to the matrix 1 2 0 1, okay, and this matrix is congruent mod 2 to the identity matrix, because after all if you read mod 2 is 0, so that means A2 and A2 inverse, okay, they are the same mod 2, therefore, but you know lambda is supposed to be invariant under congruence, I mean elements congruent to identity mod 2, therefore lambda of A2 is equal to lambda of A2 inverse, okay, that is the reason, so so you see A2 squared belongs to the congruence mod 2 subgroup, because you see the A2 squared, so if you want I will write down A2 squared of tau belongs to PSL 2Z congruence mod 2 subgroup, okay, because it is congruent to identity mod 2, and therefore lambda of lambda of A2 squared of tau, that is A2 of A2 of tau is equal to lambda of tau, okay. Now what you do is you replace A2 of tau by some tau prime, okay, then you will get lambda of A2 of tau prime is equal to lambda of tau, which is A2 inverse of tau prime, so that is how you get lambda of A2 is lambda of A2 inverse, okay. So this needed some explanation, okay, but essentially we are using these, and then the last one is also lambda 2 minus 1 by lambda 2 corresponds to this one no this one, so it is lambda of A4 of tau 2, so this is just lambda tau 2 minus 1 by lambda of tau 2 that is lambda of A4 of tau 2, and you see lambda of A4 of tau 2 is also equal to lambda of A6 inverse, okay, and the only thing that is left is this, you can recognize that this is this that corresponds to this one, so it is lambda of A5 of this is 1 by lambda of tau 2, this is lambda of A5 of tau 2 and interestingly this is also lambda of A5 inverse of tau 2, the reason being that A5 squared is also congruent to identity mod 2, see A5 if I write it down here, see A5 of tau is the transformation tau by tau plus 1, and that corresponds to the matrix 1 0 1 1, okay, and if you take A5 squared you will get so A5 squared will correspond to just multiply this, take the square of this matrix, multiply it with itself and then read it mod 2, so you will end up with identity, okay. So in fact it will correspond to, so let me write it down, 1011 times 011 if I multiply it I will get so this is congruent to 1001 mod 2. So the model of the story is a phi squared is also in the congruence mod 2 subgroup, therefore lambda of a phi is the same as lambda of a phi inverse. now you see look, now I claim we have got the proof of the corollary, because you see lambda on omega and on if you take omega and omega prime and okay, and you take part of the boundary, lambda is actually biholomorphic, okay. So you see I have my tau 1 and tau 2 are somewhere here in D, okay. So they may both be here or they are here. In any case you take tau 1 and tau 2 here, okay, then all the images of tau 1 under these 6 transformations are the images of, so let us assume that tau 1 is, let us say tau 1 is in this unshaded part, okay, then there are two possibilities for tau 2. Tau 2 may be either in the shaded part or it may also be in the unshaded part. If tau 2 is in the shaded part, then it is going to be in one of the if you move tau 2 by any of the if you move tau 2 by any of these, it is going to go into the other shaded parts, okay. And similarly if tau 2 were in the unshaded part, then it will be moved by the inverse, by all these inverses into the other unshaded parts. So the model of the story is that no matter with what tau 1 and tau 2 you start with, okay, this quantity these either the images of tau 2 under a1 through a6 or the images of tau 2 under a1 inverse through a6 inverse is going to completely lie in omega union omega prime, and then and of course you may have to include part of the boundary, of course you have removed 0 and 1, okay, but lambda restricted to this is actually injective, okay, lambda restricted to that is actually injective, okay, and that injectivity will force that you see it will tell you that tau 1 has to be either a1 of tau 2 or it should be the image of tau 2 under either one of these ai's, or it has to be the image of tau 2 under one of these ai inverses, okay. But then tau 1 and tau 2 that may, but on the other hand tau 1 and tau 2 are in D, and all these ai's and the ai inverses are of course PSL2Z elements, and the script D is a fundamental region for PSL2Z, namely you cannot have two distinct elements in a PSL2Z orbit inside D, and that will force tau 1 equal to tau 2, and that will give you the fact that j tilde of lambda of tau 1 is equal to j tilde of lambda of tau 2 with tau 1 and tau 2 in script D implies tau 1 equal to tau 2, okay, that will give you the injectivity, okay. So let me draw a line here, and then I will just write here that j tilde that implies tau 1 is equal to tau 2, okay, that is the end of the proof. So essentially you see there are two ingredients, one is understanding the mapping properties of lambda under these 6 transformations and their inverses, and the other thing is this theorem, okay. So therefore the only thing I am left to do is to prove this theorem, okay. So how do I do that? That is done by pure calculation, so let me explain that next, and then we will be completely done with the statement of the theorem that the Riemann surface structure on the set of holomorphic isomorphism classes of complex tori is biholomorphic to the complex plane, okay. So let me try to prove this theorem. So proof of the theorem so it's so let me explain. It involves some computation which you can, I'll tell you what's going on and you can write it down for yourself and check that indeed what I'm saying is true. So what you do is first I mean it's a purely a brutal force computation, but then it's it is driven by the foresight that by the foresight of Galois theory. Okay, so so what I do is I start with suppose, so so I have j of lambda 1 is equal to small j of lambda 2. So what I will get is I will get well I will get 4 by 27 lambda 1 squared minus lambda 1 plus 1 the whole cube by lambda 1 squared 1 minus lambda 1 the whole squared is equal to 4 by 27. Same expression with lambda 2. This is what I will get. Now what you do is that you cancel off the 4 by 27 and simply cross multiply to get a formidable looking degree 10 equation in lambda. It's a polynomial of degree 10 in lambda, it looks quite formidable. So so you factor you just cross multiply this, okay, and then the first thing you can see is if you play around a little with it, then you will see that it can be factorized. So you see so you see that cross multiply and factorize, what you will get is you will get lambda 1 minus lambda 2 into I think the other factor is lambda 1 plus lambda 2 minus lambda 1 lambda 2 into, you will get a third expression which looks a little formidable, but let me write it out. So it's 1 minus lambda 1 squared into 1 minus lambda 2 squared minus lambda 1 squared lambda 2 squared into lambda 1 squared into 1 minus lambda 2 plus lambda 2 squared into 1 minus lambda 1 minus 3 lambda 1 squared lambda 2 squared into 1 minus lambda 1 into 1 minus lambda 2 is equal to 0. This is the factorization you will get. Okay, so I will tell you what is the motivation. See, you want to say that lambda 1 belongs to this. So for example, you want one of the possibilities lambda 1 equal to lambda 2, so you should expect lambda 1 minus lambda 2 to be a factor, and obviously if I in this equation if I plug instead of lambda 2 if I put lambda 1, the equation is satisfied. Therefore you should expect lambda 1 minus lambda 2 to be a factor, and it is. Okay, and the other possibility, see this possibility, okay, is the possibility that if you write it down, if you write this down, see what you will get is lambda 1 plus lambda 2 minus lambda 1 lambda 2 is equal to 0. See, this is if you divide throughout by lambda 1 lambda 2, you will get 1 by lambda 1 plus 1 by lambda 2 is equal to 1, and you will get 1 by lambda 1 is equal to 1 minus 1 by lambda 2, which is lambda 2 minus 1 by lambda 2. So you see this being 0 corresponds to this possibility, this one, lambda 1 taking the value lambda 2 minus 1 by lambda 2. Okay, so there are only finitely many of these, and you have to cleverly guess which one of them you will get out as a factor, and this comes out quite easily. So you see, therefore these two correspond to these two possibilities, this one here and this one here, alright, and then lambda 1 minus lambda 2 equal to 0 gives lambda 1 equal to lambda 2, and lambda 1 plus lambda 2 minus lambda 1 lambda 2 equal to 0 gives lambda 1 is equal to, as I wrote down, lambda 2 minus 1 by lambda 2. So you have got two of these guys. Okay, now so what is left out is the formidable expression inside, okay, which is you can see it's yeah, it looks degree 7, okay, and so what you do with that, is, well, you notice the following thing. You will notice that if you put so you know the expression in the square brackets, if you put lambda 1 lambda 2 equal to 1, or if you put lambda 1 plus lambda 2 equal to 1, it will vanish. Okay, the expression within vanishes if lambda 1 plus lambda 2 is equal to 1, or lambda 1 lambda 2 is 1. Okay, and you can see this corresponds to the case lambda 1 plus lambda 2 equal to 1 corresponds to the case lambda 1 is equal to 1 minus lambda 2, and the lambda 1 lambda 2 is equal to 1 corresponds to the case lambda 1 is equal to 1 by lambda 2. Okay, so you get these two. Okay, and so the trick is, what you do is put put t equal to lambda 1 plus lambda 2 minus 1, and s is equal to lambda 1 lambda 2 minus 1, then you should expect t and s to be factors. Okay, and transform the whole equation inside the brackets into an expression in terms of s and t. So what you will get is, essentially you will get the following thing. After some simplification, you will end up with st, we get the expression within the brackets as, well, it turns out to be s times t, s into t into what you have here is s into t into s plus 1 into s plus 3. You get this. Okay, so either this is 0 or this is 0, or this expression is 0, but this expression is 0 will either mean s is 0 or t is 0, which gives you these two possibilities, namely lambda 1 is equal to 1 minus lambda 2 or lambda 1 is equal to 1 by lambda 2. So the only thing that you will have to worry about is the expression within this square bracket. Okay, so let me put flower brackets so that I can write it like this. So s equal to 0 gives, so let me write that s is t equal to 0 gives lambda 1 is equal to 1 minus lambda 2, and s is equal to 0 gives lambda 1 is equal to 1 by lambda 2. Okay, so I will have to only worry about the expression inside the square brackets. So write out the expression within the square brackets as a quadratic in lambda 1 and solve. Okay, write out that expression inside the flower brackets as a quadratic in lambda 1 and simply solve using the good old high school formula for a quadratic equation, and lo behold, what you end up is either you will get either lambda 1 is equal to lambda 2 minus 1 by lambda 2, which is this one again, or you will get 1 by 1 minus lambda 2. Okay, so that's it. So the point is that because you already know that this is what you should get, you can guess the factors by substituting properly. Okay, so the moral of the story is that having known this, in advance helped, but this is not something that has come out of nowhere, it is not just a bunch of tricks, but it is actually a statement of the fact that this mapping lambda going to j from p1 to p1 is a Galois cover with Galois group, the symmetric group on 3 elements. Okay, so probably in the exercises or in a later lecture I will expand on it. Okay, so all I want to say is that this comes from Galois theory. Okay, but having known this, factorizing it is not a big deal. Okay, so that finishes the proof of this theorem. Okay, and therefore we can breathe a sigh of relief. We have finally been able to prove this statement that on the set of holomorphic isomorphism classes of complex tori there is a natural Riemann surface structure, and that Riemann surface structure is actually the biholomorphic to the natural Riemann surface structure on the complex plane. Okay, so I will stop here. What I wish to do here onwards is try to explain how these complex tori are elliptic curves. Okay, so I will have to give the algebraic aspect. You can already see that in the fact that j tilde restricted to D is injective already brought up this a lot of algebra, and I told you this has got to do with Galois theory. And if you also look at this equation, you see that this is a cubic equation in 2 variables. Okay, so it is of the form y squared is equal to 4x cubed minus g2x minus g3. It is a cubic equation in 2 variables, and this is so it's algebraic, and it defines what is called, and its zeros define what is called an elliptic curve. Okay, and what I'll try to show in the later lectures is that every holomorphic complex torus is actually an elliptic curve. Okay, and so that's how this is a very special case of the more general statement that you take a Riemann surface and you put one topological condition that it is compact as a topological space, then lo behold it becomes an algebraic curve. Okay, it becomes a curve which is given by a neat algebraic equation. Okay, and this is the first case, the case of genus 1, namely the case of a complex torus, where you are able to directly verify it because you have this differential equation. Okay, but but for genus greater than 2 things are more difficult and they require more theory. Okay, so I will stop here.